As we're dealing with solutions, the tail of the solution is as much about the solvent, meaning the water, as it is about the solute, the thing that we're dissolving in solution. And to really highlight this, we're going to begin with a question: how does water move in the body? We've learned that our bodies are a really high percentage of water, which does need to be transported around all the time. We sweat, we urinate, we drink water. Water is constantly in motion for, animal life forms. So how is water transported around the body? And a great rule for this is to remember that water follows salt, or how I've heard it before, salt sucks. The presence of salt will draw water toward it, and what we'll see is that water is going to follow the salt pretty much. And so this is due to what's called osmosis. And what is osmosis? I recommend maybe you take a minute to pause here and see if you can come up with a definition of osmosis. We'll describe it a bit further as well. Okay, hopefully you've paused, written a few things down maybe. Osmosis is the movement of water across a semi-permeable membrane. And so when we say semi-permeable membrane, we basically mean something that water can get through that other things can't get through. And this water will move from an area where there's more water to an area where there's low water. And again, remember that when we're dealing with solutions, it's not just how much solute. It's the relationship between solute and solvent. So when we talk about a place of high water, that's a dilute solution. There's more water in that solution. Area of low water, that's a concentrated solution. Less water per amount of solute. Remember those coffee cup examples we had before. When you're talking about a little bit of sugar versus a lot of sugar, well, that's one way to think of concentration. But another way is to say, well, the first sugar has a lot of coffee with it, and the second sugar has less coffee with it. So it's about a relationship, and I think that viewing concentration in this way can really help, and it shows by this definition that water is going from where there's a lot of water to less water. It wants to even out the water. So how exactly does this work, right? So let's look at this example where we have a container with a semi-permeable membrane, and the blue dots are water, and the red dots are some sort of a solute particle. And in the middle, we have a semi-permeable membrane. So if we look at this example, what we can see is that we have less solute on the left compared to on the right. And another way to think about this is that we have more water on the left compared to less water on the right. And even though there's the same number of water particles, because there's more solute on the right, that means that there's less water percentage-wise, right? This could even be like the very minimally sweet coffee on the left and the really, really, really sweet coffee on the right. So when this happens and separated by a semi-permeable membrane, that water is allowed to pass through, but not the solute, what we have here is that water will go from where there's a lot of water on the left to where there isn't a lot of water on the right. And this is going to happen until the right side raises up to a certain height compared to the left side. Because as the right side is gaining in height, it is pushing the water back by virtue of it being higher. But osmosis can defy gravity because the water wants to go from the watery side to the less watery side. It wants to go to the side with a little bit of salt or sugar to the area with a lot of salt or sugar. Traditionally speaking, though, when we're controlling these osmotic pressures, which we'll talk about soon, it's very often salt. So assuming that the red solute is salt here is not such a bad thing to do. The water is being drawn to where there is a lot of salt up to a point. So that gets us to osmotic pressure, because when things are transported, like the water across this semi-permeable membrane, it does so because it feels a pressure to go from one side to the other. And that's our osmotic pressure. And this can be defined as the force exerted by the solute particles that pulls the water across, or the pressure required to stop the movement of water across the semi-permeable membrane. So these are a little bit technical in definition. I think that what's really important to recognize as we go and look at this picture again, that when we have this semi-permeable membrane, osmosis wants to happen. It's almost like there's a pump that's pushing the water from the left over to the right. And if there's a pump, it must be acting with some amount of pressure. So Osmosis occurs because there is a pressure to this osmotic force. And again, right, this is pretty much the same picture as before, but now what we're putting here is the back pressure. And that again is because of the height of the water, right? So osmosis happens, we have these two different concentrations. The water wants to go from left to right, and when it does so, it raises the height on the right, but that height on the right makes for additional pressure there. When the force of the two is equivalent, so the osmosis going from left to right is equal to the gravitational back pressure going from right to left, now we have some sort of equilibrium. This isn't totally needed to be understood in total physical depth, although it is a really important physical principle if you take further courses. The idea, though, is that osmosis is driven by some kind of force. That force comes from the water wanting to go from the watery side to the less watery side, or in more practical description, from the side with less salt to the side with more salt.